So in the last class, we started discussing the concept of timing. Basically, for the first time ever, we started seeing that in hardware, logic gates may not be perfect. So like when you assume that you provide two inputs to a logic gate and you expect a certain output based on the combination, because it is supposed to be a combinational circuit, that may not be the case because of the delay. So not all the inputs may appear at the gate at the same time, and that can lead to some strange outcomes, right? And that's what we started discussing. We didn't really talk too much about it. We started discussing the concept of delay first, that hey, when you provide an input to a logic gate and try to get an output, there will be a delay associated to the input and output. So the output will be available after a certain time, after the input is finalized. And then we discussed the concept of fan in, like the number of inputs in a logic gate, and fan out, the number of output from a logic gate. Okay. And we discussed that if you have more inputs coming in, you'll have to encounter delay, obviously. And when you're trying to drive more outputs, same thing, you'll have to encounter delay, because no matter whether it's the input or output, there will be capacitors. And I discussed that it takes some time to charge up the capacitors or discharge the capacitor. So when you try to go from low to high voltage, that is like charging up the capacitor. And when you're trying to discharge node voltage by going from VDD to 0, essentially you're going through the capacitor again. So for both scenarios, there is a delay. So, and we categorize it based on the rise time and fall time. If the output is going from high to low, we call it the propagation delay for high to low. If it is going from low to high, we call it propagation delay for low to high. And they could be different, as I told you, based on the design. And the way we report them is as average. And the way we measure it from the time diagram would be from 50% point to the 50% point of the output, input versus output. All right. And then we also talked about the concept of slew rate, which is nothing but this rise time and fall time. And the way we calculate rise time and fall time would be 10% to 90% point for the output. And this is your rise time. This is, say, fall time. This is your rise time. And together they're called slew rates. All right. And then we started discussing this slide where for the first time ever, we started considering the fact that outputs will not be readily available as soon as you provide an input or a set of inputs. And then we saw, I think very quickly, and I will repeat that today right away, that could lead to some strange output. So imagine this is outputs is 1. Okay. And so basically you are setting one of the inputs of every logic gate. And the only way we could track the changes through a chain of logic gates would be by making everything static except for one, right? Otherwise, if multiple inputs are changing simultaneously, it is extremely difficult for you to keep track of, the node voltages. So we put this to 1, we make this 0, we make this 1. So these are static, they're not changing. The only thing that is changing now is A, as you see, is going from 0 to 1. And I'm going to very quickly show you. Please pay attention to this. These are examples to illustrate the fact that delays could lead to possible disasters, essentially, right? And there is nothing special about this particular circuit. So if you don't pay attention, you'll have to read through this text or go through the textbooks and whatnot, right? I chose some examples that are hopefully meaningful and related to whatever we learned before and we will be learning after. So if you pay attention during class, it will be helpful for everybody. So notice that imagine we start with a 0 input to the A node, right? So that means you have 0 here, you have 1 here. What should be the output of this AND gate? 0. We expect it to be 0. And that's what you see here. G1 is 0, essentially. This is your AND gate output. But then A changes from 0 to 1. So these timing diagrams are essentially like a story. So you have to follow along, right? If you miss one, everything else will basically not make any sense at all, right? So, all right. So you transition from 0 to 1. So when we see that this guy is now 1 and you have 1 and 1 at the input, so the output should be 1. That's what we expect, but that's what you don't get. Notice your A is 1 here and B was always 1 to begin with, but G1 is 0. Why is that? That's where your delay is showing up. Yes, G1 got the news that, hey, something changed to the input. A is now 1, so I should start changing the output. But the output will not change instantaneously. There will be a delay. And this is what you see. So G1 eventually changed from 0 to 1, but it took some time. And for this example, it's like 20 nanosecond, for example, right? So this is the delay. So when you see this output showing up, eventually, right? Eventually, there has been a situation where, just take a look at this timing zone. Your input was 1 and 1, but your output G1 was 0, which is completely counterintuitive for an AND gate, don't you think? So that's exactly what I'm trying to point to. Uh, Although when we write this truth table, when we talk about the logic diagrams, we assume that, hey, for this combination of inputs, your output should be this. Assuming, and that is called the steady state output. So when you give enough time to the system to stabilize, that's when you get the logical output. But as things change throughout the timing diagram, you don't see the changes reflected right away. Now, what that leads to is, when you look at a chain, that leads to further delays down the line to the final output. Let's see G2. Let's see what happens to G2, right? I hope you understand the reason behind this zone. That doesn't make sense in terms of logic, but practically, it is basically just a shifted version. Okay, now let's see what happens to G2. So this guy was 0 to begin with. And let's take a look at this. Imagine this is an OR gate. If this was an OR gate, even if you have just one of the inputs 1, your output should be 1. But it is not an OR gate, it is a NOR gate. There is a bubble at the output, you see that? So basically, whatever should happen to OR gate, you should just take an invert of it, right? So let's keep that in mind, just for the sake of it. So to begin with, G2 was 1. Why is that? What was G1? G2 doesn't know what's going on with A and B. It only considers what's going on with G1, because that's the input for G2, for this logic gate, and G2 responds to G1. So G1 was 0 to begin with. Notice that this was 0. The other one was also 0. For an OR gate, when both inputs are 0, your output should also be 0. But this is an OR gate, so it should be 1. That's what you expect. And that's why G2 was 1. All right. But notice, at some point, G1 becomes 1 now. So this guy now becomes 1. So 1 and 0, in terms of OR gate, should give you 1. But in terms of NOR gate, it should give you 0. So now your output should change to 0. But notice, there is a further delay. It doesn't respond right away. Ideally, it should have been 0 right here, but it doesn't do so. It takes some time to eventually get to the output, the final output. Does that make sense, folks? So if I try to point, I should probably draw an arrow showing that, hey, this transition is linked with the transition here. And this transition is linked with the transition here. Can you now see this? So that's how you correlate. But imagine when you have like millions of signals going through your computer chip, and they are all haphazard here and there, right? How do you keep track of all of them? And yes, this is an idealized example where I'm making just one of the input switch and the others are all static, right? Even then, it could be challenging if I don't explain this properly. But when all the inputs in practical situations, everything will change simultaneously, right? So you need some mechanism in actual circuit design to make sure. Okay, let's take a step back for a second. Let's take these examples for the practical value. Imagine you are an engineer trying to design something. You just finished learning Boolean logic and the world sounds fantastic. You could represent anything in terms of logic. But then you see nothing works because of the practicality, because of the delay, all of your outputs are random. Like when you have millions of gates and they all have random output, you cannot keep track of all of them, right? So you encounter a major hurdle in hardware implementation. In terms of software, in terms of math, everything makes sense. Boolean algebra, all perfect. But in terms of actual hardware implementation, where you have capacitors, you have parasitics here and there, you don't get to see the actual logical outcome. So you have to come up with a mechanism to synchronize everything, right? You have to make sure you don't have to manually keep track of all these edges. You can synchronize everything. So we will learn about those kind of circuits that help us synchronize combinational logic, which we haven't learned about yet, by the way. So let me show you how the real thing looks like. So you have those synchronization circuits, and in between you have combinational circuits. So this is combinational circuit. Before and after, you synchronize them somehow, and then there will be more combinational circuit, and you have to synchronize them again. So you don't just let them go through a random deep chain. You have to synchronize them every once in a while. So these are big part of the overall digital logic design. All right, we'll learn about them in this course, so don't worry, they're coming up. And when they do, I'll remind you that, remember I told you there will be a synchronization circuit. These are the ones that are necessary. Just imagine, without them, no digital electronics will exist because it's not practical, right? Okay, I hope it makes sense. Now let's move to a different example. This is probably going to be similar to what we have just learned, uh, just to help solidify the understanding, right? So the more we see, the easier it will get for us to eventually come up with these examples ourselves. So this is, I think, in my opinion, a simpler example. So this is an AND gate, and you have just one input driving both. By the way, this is a two-input AND gate, but you are providing the same input and copying it over to both inputs of the AND gate. Ideally, if X is 1, both of the inputs are 1, so your output should be 1. And if X is 0, both inputs are 0, your output should be 0. I mean, you should expect your output to just follow the input X. Does that make sense? All right, it should be the case. But what I'm showing you here is in one of the paths, so you basically copied it. But remember, it's one thing to copy in like software or pen and paper. It's something else to actually copy in hardware. You have to create, I told you, if there are two inputs, you need to have two metal lines. And for some reason, and I'll give you one example of what that reason might be. For some reason, this path has greater delay than the other path. So although you're trying to provide the same input to the AND gate, to the both inputs of the AND gate, essentially there is an asymmetry because one of the paths has a delay. And for the sake of it, we take a number called 1 microsecond. So 1 microsecond delay between these two paths, right? Let's see what it leads to. So this is your input X, which is transitioning from 0 to 1 and so on. So it is transitioning like this. Let's see what happens to Y. We assume that there is a 1 microsecond delay between X and Y. So notice Y will be exactly like X because it is essentially a copy of X, but it is shifted by 1 microsecond. Okay, that's how we designed it. But because of that shift, because of the shift between these two inputs, X and Y, your Z doesn't know that you really meant to give the exact same input. It basically reacts to what it sees at the input terminal. And at the input, notice here, right here, oh, sorry, not this one. This is the output, Z. Notice here, it sees Y as 0, X as 1. So its output is basically 0. Although you meant to provide X as 1, so Y was supposed to be also 1 because it is essentially a copy of X. So you expected to get 1 at the output. But because of the delay, are you still with me? I know it's super boring. I mean, especially if you cannot follow along, you feel lost, which is totally, that's why I have multiple examples. All right. And also you can follow along at home in case you miss it. All right. So my point is the exact same situation is occurring here. And here, I mean, the difference between these examples and the previous one was you had multiple gates, one gate driving the other. What I'm trying to tell you is even if you don't have multiple gates, you have the exact same input and trying to provide them through two different physical channels. That's the whole point. Even if you take the same input and copy it over multiple times, there will be different delays across different routes. Yes. That's a good question. Yes, I'm going to talk about it. Thank you. All right. So, are you guys still with me? Tell me. Okay. So, apparently, as you see, because of this delay, your output, final output Z starts showing some weird results. And again, before I talk about this, let me clarify. This epsilon is, let me zoom in a little bit. Can you see this now? Okay. So notice, what is the difference here? This is the difference between the Y transition and the final Z transition. All right. Why are we taking the difference between this? Because which of the inputs are the limiting factor? Is the limiting factor? Can anybody tell me? X, between X and Y, which one of these is the limiting factor, folks? Why do you think so? Because Y arrives late. So X is already ready to go. But you are basically, your logic gate is responding to a change in Y, not a change in X. So that's why we can say that this transition is a direct response to the transition in Y, because X was ready, like X has been ready, right? So the delay, if you measure the delay from here to here, this will be an overestimation. Do you guys all agree with me or no? So what is the real delay? The delay is, this is the change that led to this transition. So you need to take a difference between this transition and the final output transition. Does that make sense, folks? Okay, so that is the propagation delay. All right. And we represented it with epsilon in the textbook. All right. Now, I want to also highlight one thing here. So you know, notice this region. Your input X is 0, your Y is also 0, and Z is 0, as it should be. So it shows when the input remains stable for a while, your outputs are all good. That's exactly the point. The challenge occurs when transition occurs. During transition, it takes some time to charge up the capacity. Do you guys remember the current flowing through a capacitor? C dV dt. Okay, when the voltage stays constant, what is dV dt? Rate of change of voltage. What is that? 0. So no current through the capacitor, charging or discharging. So apparently no concept of charging or discharging a capacitor, no delay. So that's why during DC mode, when nothing is changing, you are all good. But every time when something changes, for example, your voltage goes from 0 to some value, say 0 to 2 volt. So there is a transition here. There is a dV/dt. When there is a dV/dt, there is a C dV/dt. That means capacitive current. So there will be charging and discharging. That's why there is a delay, right? So only during transitions of the input, there will be situations like this where there will be a delay. I hope it makes sense to all of us now, right? All right, let's move on to the next concept called hazards in combinational logic. Obviously, as the name suggests, these are unwanted phenomena, but as engineers, we'll have to be mindful. You cannot just be, someone with theory only, because we are supposed to be engineers and we have to make things work. So if you just design based on pure theory and idealized situations, when you design something, nothing will work. They'll all be like random outputs everywhere. So obviously engineers didn't know this when they started. They designed chips and they didn't work, and they figured out why they didn't work, and they try to counter these issues. This is one example, and this is just 200 255, right? This 200 level course, as you can imagine. So the higher you go, the more challenges you learn, and you will wonder, hey, okay, so if I dropped out, say if I stopped learning about this digital electronics after 255, I mean, and then try to be an engineer, I would have done nothing at all, because I wouldn't know that, okay, this is not the end. There are many other things. Without doing that, nothing will work. So you keep learning it. This is the fun, honestly. So you'll think that, oh, we figured it out. We figured out all the problems. And then there are new problems, which appears to be the limiting factor. And next year, there will be new problems. So that's the life of an engineer is. You solve problems, essentially. Okay, so here is one problem to think about. Hazards are situations where the output changes in a way that is not logical, okay, that you don't expect based on Boolean logic. And we have seen some examples already. What you saw here, it's essentially like hazards, but I didn't categorize them that way. But there are specific categories of hazard that we talk about. Static 1 hazard, static 0 hazard, and dynamic hazard. And what do I mean by that? First of all, static represents the output was supposed to be stable. It wasn't supposed to change at all, but it changed. That's called static Y1. So the output was supposed to be 1, but for a moment it changed to 0, and then it went back to 1. It's fine now, but there was a hazard in between. Folks, do you mind if, say, the output was supposed to be 1, but it changed to 0 for a while and then went back to 1? So things are good. Do you care about that 0 transition or no? Why should you care about the 0 transition? It just changed back. I mean, it made a mistake, but it came back to the regular level. Why do you think that can be a challenge? Yes.
The delay of other elements just so happens to end up when it's 0.
Yep. Exactly. So remember, they don't work in isolation, right? They are connected to a big chain. So if there is a transition, how will the next stage know that this is just a, dummy transition? It's not supposed to happen. It will propagate that change through through the logic, paradigm. Like everything will change essentially, although it wasn't supposed to change. So you will end up with random states throughout your chip, which is like can be destructive to the overall logic, as you can imagine. So I told you there are checks and balances. There are stages that help us synchronize. So we figured it out. No worries. Things work. But we have to identify that there is an issue like this, and only then you can design countermeasures. And honestly, in this lecture, we'll learn one simple countermeasure. This is not the countermeasure, but this is definitely a possible countermeasure, right? That we'll learn in this lecture. So this is one example. You were supposed to get 1, but momentarily you got 0, and then you went back to 1. This is static 1 hazard. Static 0 will be exactly opposite. You are supposed to get 0 all the time, but momentarily you got 1, and then, it's like a spike at the voltage. Okay. And then finally, dynamic hazard. Dynamic hazard represents your anything that has dynamic in it shows that there is supposed to be change. All right. So you are expecting a change at the output. So the output was supposed to go from 0 to 1 or 1 to 0. So both are okay. You are expecting a change. Yes, the change occurred, but the change didn't occur in a single transition like this, a single transition. No, it occurred with multiple iterations. Like, okay, it went to 1 and then went back to 0 and then went back to 1. So it eventually stabilized, but it took some, back and forth to get to that level. Okay, that's what you don't like. You might be wondering, okay, why are we being so picky? There are many reasons. First of all, during this transition, as I just keep stressing, everything will be treated as logic change and they will be propagated. So that's one challenge. The other challenge is if you care about energy, every time there is a transition, there will be charging and discharging of capacitors. And think of it like, okay, you have to fill the capacitor with energy and discharge that somewhere. So every time there are additional transitions, there will be additional energy drainage. You may not care about one capacitor charging, but think of billions of components in a chip and you're charging billions of capacitors here and there. This is definitely a crazy situation to be in, right? Unless we address this properly. So we don't like this unwanted transition. That's why they're called hazards. You don't like them. And by the way, read this at home, this paragraph at home. This is only for you to, refer back when you are revising. But I'm explaining this verbally anyways. So I hope we all understand the 3 types of hazard that we see. This is basically a categorization. Static 0, static 1, and dynamic hazard. Dynamic hazard can be 2 types, 0 to 1 and 1 to 0, but doesn't matter. Both are dynamic hazards. Okay, one example, and basically, honestly, we have seen this example in the couple of slides ago. I didn't just name them as hazard, but they were hazards essentially, all right? This is just one other example, one other final example using time diagram to now identify a one hazard. Can we do this together now? Can we address it as one hazard and see why this is a one hazard? This is essentially the last example that we'll see, so don't be too bored. All right, so let me first clarify why the output was supposed to be 1. Notice this is an AND gate, this is another AND gate, and you are providing input B to both of them. There's just one difference here. There is an inverter in between, right? Other than that, it's pretty much the same. All right. So when I try to come up with this functional outcome, can I write D equals AB prime, folks? Can I write it? How about E? Can I write E equals BC? So essentially, this functional output, since this is an OR gate, will be AB prime plus BC. As simple as that. Okay. Now, imagine a situation where A and C are both 1. That's what we are considering here. We said, like I said, the only way you could follow the train of waveforms would be by setting some inputs as constant. And that's when you can track the others. So let's imagine that we set this to 1. Okay, so if A and C are 1, and this is the situation that you see here, by the way, and it's mentioned in the text, if you can read it. Okay, so A and C are 1, so you can just replace them with 1. What you get here, F equals B prime plus B. What is B prime plus B, folks? 1. It should always be 1, right? Okay, notice, when B changes from 0 to 1, will the output change at all? As long as A and C are both 1, your output shouldn't care. It should always be 1. Can we agree to that now? Okay. Okay. All right. So the output should be insensitive to the change in input B. That's how we set up this circuit. By the way, notice now we are choosing the circuit to explain this situation. But imagine the very first few engineers who encountered some random output here and there and had to somehow relate it back to this phenomena. Right? You have no idea why the outputs are doing what they're doing. So you have to somehow, this is called debugging. This is a major part of engineering life. And trust me, whatever I tell you, when you go and work as an engineer in your career, you'll encounter something that you were never taught. So don't take the courses with their face value. Oh, we are learning everything. You're essentially learning how to learn. Right? You are seeing examples from other people who figured out problems and solved the problems. It feels like, oh, anytime there is a problem, we figure it out. But you don't see the timeline. That's why the history matters. Maybe it took them like 5 years to figure it out. Yes.
Time to test these nanoseconds, or they just
That's a good question. First of all, these nanosecond numbers, don't take them too seriously, because this is a good question. Like maybe few decades ago, our chips were not that fast to measure in like nanosecond, for example, microsecond, millisecond. That's fine. These are like random numbers taken from the textbook because these are relevant to modern technology standard. Now, millisecond, microsecond doesn't even fly anymore. So that's why these are like dummy examples. And there are many other things. If you have questions later on, we are not showing rise time and fall time. So none of these are ideal. So for example, this is never going to be, a transition can never be this abrupt. It is always going to be like this. As I told you, there will always be right. So we're ignoring many stuff, honestly. Uh, to be very exact, the modern ICs, rise time and fall time is in few tenths of picosecond, not even nano, like very fast, picoseconds. So, right? But that's besides the point. We could always use T1 and T2 and T3 to just kind of normalize everything. Okay, so just keep that in mind. So this is a chain that shows you that this output is supposed to be insensitive to the input chain. But hold on, this is your final output. There was, yes, ideally it's 1. It is more or less okay, but there was one glitch. And that's exactly what it is called. It is called a glitch. Okay, and this is known, like glitch analysis is a part of digital engineering, by the way. You can search on Google, like glitch analysis is a part of it. When you see glitches at the output that you cannot explain, you try to reverse engineer and find the source of the glitch and you know, improve your circuit design in a way that you can get rid of the glitch. I mean, for modern digital IC, things are mostly figured out now. But when you get to a new technology platform, you have to look for glitches and solve those glitches. It's kind of like exactly an analogous situation as software engineering. Okay, so when there is a glitch or like what they call is a bug, right? When there is a bug in the code, you somehow see it in some output. Some, not every output. Most outputs are okay. Every once in a while, for a given combination, you get some errors, and you try to debug, and that's exactly the term, debugging, right? And for hardware engineering, it's exactly the same. You look for glitches, which are symbols of something you missed in the hardware design, and you try to go back and improve the hardware design to avoid this situation. All right. So by now, okay, let me just finish explaining this. So notice your input B changed here. Input B. Tell me one thing. Should your output care that B changed? Based on our discussion, it shouldn't. It should always be 1 because your A is 1 and C is 1. So we shouldn't care what happens to B. But let's see how that B transition changes, goes through the chain. Number 1, when B changes, that leads to a change in D. D is still sensitive to B, by the way. F is insensitive, but D is still sensitive to B, right? You guys see that? So D changed, but after a while. You guys all agree? Okay. And without any loss of generality, let's assume that every logic gate has 10 nanosecond delay. 10 nanosecond, all right? Let's consider that. So this is 10 nanosecond, this is 10 nanoseconds, so 20 nanosecond. Why is that? Can anybody tell me? Yes. Thank you. Yes. Yes, perfect. So notice the signal B, it's traveling through 1 and 2 gates. And we are oversimplifying it, honestly. Every logic gate has different level of delay. Inverter delay will never be the same as AND gate delay. But this is for the sake of our understanding. So 10 and 10, 20 nanosecond. That's why you see that it is 20 nanosecond delayed because it went through two logic gates. Okay, now then what? So when D changes, okay, E should also change because B changed from 1 to 0. So this E, output E should also change. But notice E changed sooner than D. Don't you see that? Why is that? The same argument. To get to output E, your signal didn't need to go through the inverter, just one logic gate. So you have 10 nanosecond delay instead of 20 nanosecond. So the same input leading to these changes, but the outcomes are appearing at different time frames because of the number of stages. Okay. So E is settling sooner than D. Are you guys all with me so far? Okay, hold on a second. So D in this region, D is 0 and E is 0. What should be your output for that particular time frame in this situation? Output should be 0. Do you guys all agree? Okay, output should be 0. Although I just told you, your output is set in a way that it is always 1. It should never be 0. But you arrived at a situation momentarily where it just happened to be like both inputs of the OR gate is 0. Now your output should be 0. All right, so your output should respond. And you don't get the 0 right away. You see that? You get the 0 after a while. So it's like shifted again. But then everything recovers and it goes back to 1. It behaves as this. But do you appreciate the fact that whatever change you see at a certain region is not really for that particular time frame? It is coming from the stages before. And just imagine what happens in a really long chain where you have hundreds of stages. It is almost impossible, right, to keep track of which change is coming for which transition, ahead of you. So all I want you to know, honestly, I don't care about teaching you one hazard or zero hazard or something. This will not stay with you, honestly. If you can get a feel for the criticality of the problem and feel the need to solve it somehow, like if you can agree with me that this is absolutely critical. If we don't solve this issue, if we don't find a way to resolve this, we can never have a working circuit. Okay, if you guys can all agree with, do you feel that way or no? With these simple examples, right? Okay, then we should definitely pay attention to learning the, first of all, detecting the chances of this type of hazard, that, hey, there is a chance of you have a hazard in this circuit without randomly encountering. You sell something and it doesn't work, you have a return and then you figure out why it didn't work. No, Before that happens, you should figure out during the design phase that there will be a problem and then do countermeasures. And that's exactly what we're going to learn right now using K-map. So our same old friend, K-map. Okay, we're looking at the exact same circuit. And you come up with a functional output of the circuit. And that's why we learned what we learned. There was a slide in the K-map lecture. If you don't remember, go back and check it out. It's part of the midterm quiz. Sorry, the quiz before midterm. Um, so if you are given a functional outcome, how can you convert that to a K-map? You know this already. You may not remember on top of your head, but you know this. I taught you. So just revise that. So we can convert this functional outcome into a K-map. And what the K-map shows you is a distribution of ones and zeros, ones and zeros. And how do we group the K-maps? How do we group the ones in a K-map, folks? We try to, cover all of them and try to repeat as less as possible. We don't repeat without any reason, right? Do we? Okay. So if you group these two ones, you're good. You can come up with a functional output and you'll see this is exactly this one. Does that make sense to everybody? All right. Now, this K-map will show you the challenge. If you see, and these are all written here, you can read it at home later on. If you in the K-map, if you see that after you group the ones, if you see adjacent ones that are not under the same group, that is an indication of a one hazard. Does that make sense? So notice this one is grouped with a different one, and its neighbor is not grouped with itself. It is grouped with another one. So if you consider these two neighbors, they are not grouped together. And this type of situation basically leads to one hazard. Okay. And basically people figured how can we represent this type of situations using K-map? And that's how they realized that, okay, this basically represents wherever you have neighboring ones that are not covered under the same umbrella, under the same grouping. So how can you, overcome this situation, folks? The solution is easy. Ready to hear that? Okay. Simply by pairing them up, you can make sure that even with these delay situations, yes, the delays can lead to these havocs, these challenges, but you can always create a additional condition that even with these delays, your outputs will always be stable. And let me show you. Let's get to the next. So this is essentially exactly what we saw before in the previous slide. And this is the next, new slide. Can anybody tell me what changed here in this K-map? This should be the exact same system, but something changed here. Yes, I chose to use an extra group. Can I do that without changing the logical outcome, folks? Did I tell you that? If you take more than you need, the outcome will not change. You'll have suboptimal. What do I mean by suboptimal? In terms of number of gates, number of inputs, size of the hardware. Yes, it will be more, but you'll have glitch-free, circuits. Does that make sense? So we looked at the absolute optimization where you minimize that using K-map and we ignored everything else. Now, as we see more and more issues, remember when we looked at multi-output gates, we sacrificed the functional output to group them in a way that you can share the logic gates. So that's an additional strategy. Now we're looking at taking up extra groups than necessary. So if you add this extra group, you can then, I'm not going to go through this in class. You can look it up at home. Go through the exact same exercise. Set A equals 1, C equals 1, and transition B. And you'll see there will be an additional channel completely eradicating the changes in B. So your output will always be 1. Just look it up. Just, put some random numbers and then see how that chain works. So, by the way, for this additional circle, I have an additional term. That is the cost. So you need an extra AND gate. And instead of having a 2-input OR gate, now you have a 3-input OR gate. So your number of inputs increased, your number of gate also increased. So that's the cost. But what is the benefit? The benefit is you no longer have to worry about, this glitch, this hazard per se. Are you guys all with me so far? I told you I'm going to show you a solution, maybe not the solution, of course. You're not, yes,
Some, I know we have like some like optimization steps and all that.
right.
So if we optimize this, then we will reintroduce the hazard. Right?
Exactly, exactly. That's a good question. See, this is a chicken and egg problem again. So our strategy, blind strategy, is always optimized to the fullest. But when you do so, you end up with a situation that could lead to other issues. So don't always optimize to the fullest. So remember, as human beings, we might, at some point, as you keep learning this challenge, you'll get how how can we ever make it work? Remember, you have to do design automation. So computers treat everything simultaneously. It optimizes and then tests. There is a step called verification. If you Google verification engineer NVIDIA, verification engineer Intel, you'll see many jobs because they do verification. They make sure that whatever optimization you do, I mean, there are also tools for verification, right? They make sure, oh, there are these hazards present. So go back and reverse optimize, like don't optimize that degree. So you simultaneously check for issues like this. And these are not the only issues. There are many other issues that we are yet to learn. Okay. And they're all treated simultaneously. That's why you cannot just speed up uh, chip design. Like, okay, we try to be the best in chip design in the world. We'll do it tomorrow. Invest $100 billion. No, it takes significant effort to, get there. There's another question. Yes.
The same vein, I was going to ask if there was a good extent way to optimize between optimization.
Absolutely, absolutely. And I'm so happy that you are thinking it this way, honestly, because I want you to feel the frustration. Like, oh, based on what I'm learning, I feel every day that things shouldn't work. Okay. So you teach me this, you optimize, I understand that I have to optimize. And the next day you say, if you optimize, it's not gonna work. All right. And next day you say, okay, if you optimize this way, you'll in the previous lecture, we learned how to minimize the number of gates. We went to great depths to reduce the number of inputs. Remember 14 inputs versus 12 inputs? I told you if you reduce 2 inputs, there will be saving in area, significant saving in area. And today we're introducing an additional input and additional gate. So that's exactly how life is, honestly, right? There is, and my advisor, when I was doing my PhD, he used to tell us all the time, and I now understand what it means. There is no free lunch in engineering. Like you feel like you're getting something easily, that means there is something wrong. You're missing something out. So the answer is there is not one way to do so. That's why there is not one leader in the domain. Samsung, Nvidia, AMD, Intel, Mike, they all have their own strategy. They all have their own algorithm of optimization. Some do better than the others. And you keep improving these algorithms. And design automation is a multi-billion-dollar industry, right? They're big companies. Google it. Synopsys, Cadence. They're like very big players in the field. All they do, they are software players in the hardware market. So they help you, so that you don't have to manually do it. Now you're learning manually, but when you actually do it in chip industry, you do it with software. But the softwares are also coded by the engineers like you. So, they have to know the nitty-gritty details. And every once in a while, there will be a discovery that leads to the change. Like, oh, why is it behaving this way? So you need to reverse engineer and find solutions this way. Okay. Did I answer your question? So what is the take home message? You need to introduce extra term in the K-map optimization to cover neighboring ones. And I'm going to quickly show you one other example here without any loss of generality. This is another circuit. I'm not going to make you go through the boring exercise again. Oh, this is 1, this is 0, this is changing, this is changing. No. I hope by now you have got the point, haven't you? So if you go through the chain, you'll see the output will not follow along the actual trend as it should because of the delay. So how can we see that without, this is my other target, to make you bored so that you see, hey, going through the chain A, B, C input is a pain. I don't want to do that. How else can I identify that there's going to be a problem? Here is how. You don't have to look at the circuit chain. Just look at the K-map. Okay, now we are getting out of the circuit-based chain tracing and going to K-map based detection of possible hazard. And logic 0, logic, obviously logic 1 hazard occurs when you have neighboring ones, not under the same umbrella. Similarly, logic sorry, static zero hazard occurs when you look at the zeros of the K-map. Okay, if you have can you see this properly? When you have neighboring zeros, this is neighboring zero, this is also neighboring zero. And by the way, don't forget, these zeros are also neighbors. Remember I told you that K-maps wrap around both in X and Y. So basically, say this zero and this zero is also neighbor. If you think about it this way, right? They're wrapping around. So whenever you have neighboring zeros, you are gonna have static zero hazard. Neighboring one, static one hazard. So what do? You add extra terms to cover these hazards. Okay. So let's see. This is the solution. See what we are doing here. To cover these two neighbors, we are taking an additional group. Did I tell you that more zeros or ones you can take under a group, the simpler the expression would be? So I could have grouped it with just two, but I'm deciding to group it with four because I can. In case you had that question, all right? The more you take, the better. You are making sure they're under the same umbrella. Okay, what else? Notice this zero and this zero are supposed to be neighbors. So I'm taking an extra group like this. Extra. They're already covered, but I'm taking an extra group. Okay, what else? Anything else left? No, I think we covered pretty much everything. All right. Does that make sense? Do you see any other zero that is not under the same umbrella but neighbors? This is one example. I didn't talk about it. This one. See, we added an extra group to cover these two neighboring zeros. But that was not necessary, essentially, right? This was already covering all the zeros. Are you guys all with me so far? Okay. So by doing this extra thing, notice you convert this simple function into something super complicated like this, just to avoid hazard. So it's that critical. Otherwise, things will not work. Okay, you have a really optimized solution that only works when nothing changes, when the inputs are all static. Right? So just imagine the craziness in that claim. Okay. So to make sure that things work in a practical situation, we have to go through this route. This is the final slide. It's a very easy example. I'm going to end with it. Give me 30 seconds, please. This is an example of a dynamic hazard. This is exactly the same as any other hazard. If you have neighboring ones or zeros that are not covered, you have hazard. So you have to add extra term. But why is it specifically dynamic? Dynamic hazards typically occur when an input is shared with three or more other inputs. For example, C is being fed to 1, 2, and 3. Remember, when you have three or more inputs being driven by the same variable, that's when this dynamic hazard occurs, because there will be one transition here, second here, third here. When you have more than two delays into the play, that's when this dynamic hazard, the zigzag pattern occurs. Okay, but the remedy is exactly the same. So nothing new. We covered it. Just make sure you have extra terms covering these ones. That's all. Are you guys all with me? So the solution seems simple. At least we can leave in place at this for the time being. You don't like it because it gives extra area, but at least it works. All right. You'll learn better solution in the future. All right. Thank you all. We finally managed to finish this lecture. All right.